Hello, everyone. Welcome to this manufacturer showcase hosted by NYSERDA's Empire Building Challenge. Its purpose is to familiarize you with new or emerging technologies meant to facilitate decarbonizing our building stock and applicable across entire portfolios. All sessions will be recorded and available upon request, and slide decks will be sent to all attendees. Presentation will be 20 minutes, followed by 10 minutes in which the presenter will respond to your questions. We ask that you go on mute until then. And now it is my pleasure to introduce Stephen Eaves of VoltServer. Steve?
Hey everybody, thanks for giving me the opportunity to talk about our technology. My name is Steve Eaves, and I'm CEO of VoltServer. VoltServer founded a new type of power distribution technology that we branded digital electricity. In the industry, it's generically known as fault managed power. So digital electricity protocol is a way to send conventional electricity in what we call packet energy transfer format. So we send electricity in little bursts of electrical current, followed by a period that we call a data component. And that period, during that period, we're monitoring the transmission lines and checking that that little bit of energy went from a device we call a transmitter to another device we call a receiver. Coming into the transmitter is conventional AC or DC electricity, and that usually sits in the electrical room of the building. The receivers sit local. If we're talking about, say, a building in New York City, the receivers are up in the apartments powering loads. And I'm showing an induction oven here as the load all the way to the right as a sort of iconic example of what we're all after. As you know, we're all trying to decarbonize buildings, and the induction stove in our analysis and say a New York City apartment is the actual design driver. So where you might have a 5 kilowatt peak load in a New York City apartment now, just adding an induction stove can take that load up to about 13 kW, which is a very large increase in the building requirements, and it's very difficult to achieve with the existing power distribution equipment. You might have just a 60 amp main on the circuit breaker panel in the apartment. Even if you solve it there's problems down at the beginning and the middle of the building of getting the power from the street through the service entrance up to those loads. So this is a way to very quickly route power from the basement of a building up to the loads, and also to manage that power. As I mentioned, the generic term for this technology is called fault managed power. If you look around on the internet or in the industry groups, you'll see a lot of traffic about that technology. It was adopted into the National Electric Code last year in 2023, and there's 2 new UL safety standards that were formed around qualifying the equipment and the cable that goes with it. So why do people use it? It's been around a while now. We started installing systems around 10 years ago, initially in communications venues like stadiums or airports or conference centers. To date, there's 1,000 large venues that have digital electricity installations, many of them substantial installation power levels in the megawatts. So people use it because it goes in very easily using low voltage, or what we would call limited energy installation techniques. So it has the power capability of conventional AC power, but it installs like Ethernet cable. So it's conduit free. It's qualified to run in risers, so that riser closets in buildings can carry digital electricity, or data tray J-hooks. It's basically an IT installation. So whatever practices that you might use for low voltage or Ethernet cables, the same practice you use for this technology. It uses very thin cabling. The reason why is because it's a high voltage distribution technology. So the innovation wasn't so much getting a lot of power in thin lines. That's already achieved by using high voltage, as anybody could see by looking out their window at the utility poles. But the innovation was to make that safe. So sending it in packet energy transfer format allows it to be qualified as a limited power source technology. And under the National Electric Code, it can use those practices. So there's no breakers or panel boxes, AFCIs or GFIs, transformers in the DE circuit. Once you convert to digital electricity, it's one communication line from point to point, from the basement of the building all the way up to the apartment. It has move, add, change flexibility because it's conduit free and it can move around like an Ethernet cable. And it's typically used in places like 911 call centers or stadiums where they have emergency power requirements, because it allows the user to centralize the power source. So if you have batteries or generator, or even something like a solar array, it lets you put the power, the transmitter part, near that source and then distribute it widely in the building. Another real core component is integrated load management. As many of us have already found out, when we're trying to convert buildings, electrify buildings, and sort of displacing natural gas, that impact, that peak power impact, you really can't use brute force techniques anymore. You have to manage the loads, and often those loads can be managed without any effect on the customer or the tenant, right? Because if you're running the stove at peak power, you don't necessarily need to be making as much heat in the apartment, so you can turn down, for example, the heat pump. So capabilities are about 6,000 feet distance from transmitter to receiver, and I'm calling it about 8 kilowatts of power at the endpoint. So this isn't for giant electric motors, like 100 kilowatt motors. It's for smaller point-to-point distribution. But I should say that with power electronics, we can parallel and get to very high power levels. When is it not a right fit? It's not the right fit for short distribution runs. This is a power distribution technology. So if you're only going from, say, one side of a room to another, you're not going to pay off the transmitter and receiver components. Where it sort of pays back is by simplifying power distribution between those points. In a stadium, for example, conduit installations are about $38 a linear foot. So with digital electricity installations, that's less than $10 a linear foot. So if you go enough linear feet, then you pay for the equipment, and it works out very well. And as I mentioned, it's not really for very large single point loads, although we are looking at things even like powering HVAC units on the top of a building. But if you have like a giant motor in one place, it's probably not the right thing. Here's a couple of the core areas, and I should point out that as we go along in this presentation, over to the lower right, there's clickable points where you can get to case studies or white papers. And because everybody's going to get this presentation, you can then go back later and pull those things out and take a look. This is our earliest installation base, which is wireless densification. I believe about now, the majority of NFL stadiums have substantial digital electricity installations. This is an example, Hard Rock, which is a multi-megawatt digital electricity installation with hundreds of miles of distribution. And as you can see, it's really based on the expansion of 4G and 5G infrastructure. Smart buildings is an area that came a little bit later. So there's a number of hotels. We're going to look at this as a case study in a minute. This is the Circa Hotel in Las Vegas, which was about 750 rooms. I should point out that in these installations, these earlier installations were powering LED lighting, building controls, small devices, but there's still outlets that are fed by conventional electricity in these buildings. And the things like the big rooftop HVAC units at the top of the building are still conventional AC, but most of the other stuff from top to bottom is digital electricity powered, combined with a low voltage technology like 24 volt power for lighting, or PoE is another great one that we'll talk about. CEA, or controlled environment agriculture. This is what many of you might have followed a little bit. This is the movement of agriculture to indoor controlled spaces. And it's sort of, digital electricity is particularly meaningful in full vertical farming, where it's all LED lighting that's complicated. power distribution for the lights and for controls and for sensors and all of that. The common theme here is digital electricity is ideal for digitally connected venues that combine power distribution and load management or sensing and control. All those things work together to modernize buildings. Very quickly, this is a conventional AC power infrastructure, right? From on the left side, you come in with a service entrance feed to a switchboard, and in a big building, that goes up to vertical electrical risers that then break out 480 volt power into distribution transformers that break it down to 208, 110 volt feeds. So that is then brought into here. What we're showing is hotel rooms. There's also a parallel data infrastructure that's coming up with Ethernet connections or fiber connections to the IT stuff that's in that building. And that's kind of the way things are done now. If you look at the comparison, a digital electricity installation, those things are what we call converged. So you have a common riser, communication riser that's carrying both power and data. And here we're using what's called a hybrid fiber cable. This is a common thing, commonly used for digital electricity, fiber optics combined with copper in the cable that then go up into here, what we call zone boxes that then convert digital electricity back to low voltage. And in our final installations in these buildings, complete displacement of the AC, where we invert the digital electricity back to AC power for here, we're showing hotel rooms. There's still a conventional AC feed coming in or a service entrance, but the thing to remember is when you have digital control like this, and when you have such fine control over the loads, the service entrance requirements go way down, typically half or more reduction in service entrance requirements, which can be a really big deal of what we're all trying to achieve, because even if we do fix an apartment, for example, it doesn't mean that we're going to have enough power down at the street to get up into the apartments and the building. Our case study here is Hotel Marcel. This is in New Haven, Connecticut. Our customer was an outfit called Sinclair Digital that we partnered with in a number of very interesting products and projects. Sinclair specializes in the combination of limited energy technologies, specifically PoE, also energy storage and management. And in this facility, this is a fully net zero hotel in New Haven, about 165 rooms. And it has very modern energy design. There's about 300 kilowatts of solar on the hotel that is then combined with a pretty substantial battery backup system. I shouldn't say battery backup. It is an energy storage system that's balancing the renewable energy coming in, peak loads, and then it also acts as a backup power system. That is then distributed through digital electricity transmitters up to PoE switches. I'm going from left to right. And that goes to a receiver that then converts to PoE. The receiver, in this case, digital electricity is powering PoE switches. And then the PoE is then powering a bunch of loads that are in the hotel rooms and common areas, controls, communications, LED lighting, even things like shower valves and mini fridges, small devices like that. And we're moving towards larger devices like, as I mentioned, HVAC units on the roof. Comparison. So this white paper, again, you could see at the top here, you can download this white paper for detail. We really don't have time to go through all the elements here, but it does give you what is basically, switching back here a little bit, a comparison of this architecture to this one. And this analysis was done on real data that came from bids, construction bids on a property. And there was 5 bids that are used. We took the lowest bid for the work, and that bid quoted what it costs to install electrical into hotel rooms, electrical outlets. And we compared that to using a digital electricity installation using the architecture I showed earlier. And it does show a pretty substantial benefit from converting. And we do see that type of range of 20 or 30% reduction in cost in the right environment, where, as I mentioned, where you have a pretty good substantial distance from the transmitter to receiver, and there's a lot of digital devices that benefit from the load management and controls aspects, because this technology combines data and electricity into the same wires or in the same cable, and so it's ideally oriented for digitally controlling the devices inside a building. Finally, rather than converting to AC in those zone box I was showing, the world is really moving towards complete DC for devices. Some of you have probably followed this, but inside of our appliances, whether they're commercial or at home, those devices have already converted to DC behind the sheet metal of the device. So as you come in with, say, 110 or 220 volt power, it's rectified, converted to DC, and then whether it's a refrigerator or a stove, it then operates on that. So what I'm showing here is this is a really innovative outfit called InvisiCook that we've worked with. And what you're seeing on the left is an induction cooktop that is actually inducing the field in the pan through porcelain or stone countertop. And on the right is the unit or the module that's underneath that countertop. That's the induction cooktop module. And it's operating on DC. We're not converting back to AC. The receiver sends 336 volts DC into the induction unit, and then it works just fine. Actually works better than it would if it had to rectify AC. Now that is a very efficient installation, because we have a very thin wire coming up from the basement of the building up to the stove, and then very efficient conversion. So the receiver that you're looking at, the green box, is about 99.6% conversion efficiency while it's powering that induction unit. And I think that's it. We made it just about right on time.
Great. Thank you, Steve. We're going to open up for questions in a moment, but can you just scroll back to the pricing sheet that you had? Because I found that a little confusing. It looks like you're comparing $5,000 to almost $2 million, but only a $5 a square foot difference, or a $5 difference in the square foot cost. Can you clarify that?
So the left side, this study was based on a bulk bid for the building, for installing electrical into the outlets of the hotel room. And it wasn't broken down like a digital electricity system. There's just one price. And the white paper will kind of go into that. The right side is the digital electricity installation, and that one is breaking out into those zones. So that's broken out into a room cost. And then that room cost is then broken into a square foot, dollar per square foot value. And the left side, because it was a bulk bid, it's really based on the total square feet in the building, and then broken down into a dollar per square foot value. It's a fairly conservative, we think it's a fair way to look at it, looking at it as the price per room on the digital electricity side, because the distribution inside the room is more complex than the sort of average distribution in the whole building. So we think the analysis is fairly conservative. Hopefully that helps a little bit, but that is explained. The assumptions for the study are explained in that white paper that will have a link, that has a link to it at the top there.
Great, thank you. If you can just scroll to the end so that people have your contact information. And with that, if anyone wants to ask a question, please unmute. And then if you can mute yourself again so we don't have any background noise. Thank you. We have about 10 minutes left.
Hi, this is Lisa Hart from Syracuse Housing Authority in the upstate New York. You were saying that you couldn't use this for anything like a large capacity. This would be for like mostly for appliances. Is that what you were saying? Or did I misunderstand that?
Yeah, it's a little, so the way that it works is it uses communication to send power. And so it's using about a 16, anywhere between say 18 and 12 gauge wire. And each one of those wires carries, in the newest generation of the product, about 2 kilowatts per wire. And those channels, as we call them, are brought to the receiver, and the receiver converts that back to AC or DC power. But it's usually in about a 4 to 8 kilowatt chunk. Now we can go higher. We can power a big device, say, as I mentioned, like a big motor controller. But what you need to do is have electronics that then manage the paralleling of those receivers. And a good example that we were just working on is where we did power a substantial load, but we use a solar inverter, and the receivers are actually powering the maximum power point tracking channels of the inverter, and that inverter is managing the parallel inputs, the solar inverter. Did that help at all? I'm not sure I helped at all in that.
Nope, I was wondering that part. I was a little confused about, but thank you. But
Yeah.
after I saw, we'll send us the recording, so I'll be able to look at the attachment. So thank you.
Sure, and feel free. I got my email right here. If feel free to launch a question if you want that way too, and I'll respond quickly.
Thank you.
Steve, we have a similar, if not identical, question in the chat. I'll just read it. Is this suited for heat pump retrofits in multifamily buildings, or is this geared toward lower power applications?
We do a lot of low power, but today's presentation is really focused on the first one, which is heat pumps, stoves, hot water heaters inside an apartment setting. That's a really nice. Now, as I mentioned, about 8 kilowatts. If you put all those devices together at peak load, maybe it does go above 8. It could, but with a little bit of load management, we believe 6 to 8 kilowatts is perfect for, say, an apartment in New York City with load management.
Great. Any other questions? And please feel free to unmute if you want to ask a question.
I've got a question. Saul, if I can take a turn.
Please, go for it.
Sure, this is Jen from HPD, and admittedly not an electrician. This is not an area of strength for me, but following up on the previous question, if you are doing a heat pump and or full electrification retrofit in a pre-war building, for instance, can you just walk through, like, are we talking about running this new cabling like from the meter room up through the building? Like, it's a fully separate installation outside of the normal power infrastructure, right?
Yes, exactly. Exactly. Yes. We call that an overlay. So the existing panel box stays there. And this wire, it's a thin wire that comes up through the communication ducts in the building that goes to the apartment. And then in the apartment, there's a receiver inverter there that is powering the stove, the heat pump with load management that balances which, so they're not on at exactly the same time. And in the case of the stove that I showed you, like the InvisiCook product, it can go direct to the stove without even inverting. But that's how we're proposing that this be done.
And then just one last follow-up question. Sorry about the background noise, but when you get to the electric service for the building, we're still talking about adding a significant amount of load if every apartment is doing this, right? But what you're saying is the diversification of this through this equipment does not mean that your service increases that much. And again, sorry if I'm not articulating that well.
Yeah, no, I completely understand. Yeah, there's, depending how it's done, and I have to say, if it's done without any energy storage, right? Because one option on the system is to have batteries that take peak loads, which could be very useful for things like stoves, but not useful if you have long durations of heating, for example, on the heat pump side. But by load management, whatever the impact would have normally been with what I call a brute force method, where you just upgrade all the panel boxes to 200 amps or whatever in the apartments, it's much, like I said, it's maybe a half to a quarter of the impact on the service entrance.
Thank you so much.
Great. Any other questions? All right. Steve, I had a question just about the labor rates and qualifications to install this. I think it was implicit in the costing layout, but did you want to say something about the requirements or the licensing requirements for installing this and how that compares with conventional electric upgrades?
Yeah, sure. So this is what's classified as a limited energy installation. So within the electrician's grades, right, their training levels and qualifications, there's a department within the electricians that specializes in limited energy. So in New York City, if that's what we're talking about, they're licensed electricians, but they specialize in limited energy. They typically are a lower rate than what's called a wireman or a journeyman electrician. And even within, like, if you take like local 3 within New York, local 3 has limited energy as well as journeyman electricians.
Great, thank you. So last call, does anyone have any questions? All right, well, Steve, thank you very much. Looks like we had one more come in the chat. Would you be willing to put together theoretical pricing and design for a theoretical building?
Yes.
Great. So if anyone wants to reach out to Stephen Eaves, you have his email here. It is also in the invitation that was sent out. If you have any further questions or want to explore this technology further, will now end the recording of this event. Anyone who wants to receive this recording, just let me know. I'll be glad to send it to you. We will also be sending the slide deck to everyone on the invite. So with that, thank you all very much.
Thanks for the opportunity.